This question came for 2 marks in EC GATE 2018. Let's see the question. A DC current of 26 microampere flows through the circuit shown. So IDC flowing is 26 microamperes. The diode in the circuit is forward biased and it has an ideality factor of 1. Eta is equal to 1. At the quiescent point, which means the operating point, the DC operating point, the diode has a junction capacitance of 0.5 nanofarad. So the junction capacitance, which would be small signal capacitance in fact, is 0.5 nanofarads. Its neutral region resistances can be neglected, which means the P side and N side, which are neutral regions, their resistance can be neglected. Assume that the room temperature thermal equivalent voltage is 26 millivolts, which is Vt is equal to 26 millivolts. For omega is equal to 2 times 10 power 6 radians per second, the amplitude of the small signal component of diode current in microamperes correct to the 1 decimal place is dash. Now if you look at the circuit, there is a DC source and an AC source. But here we are going to do a small signal component of diode current. When we do small signal analysis, we may call the DC source as 0. So the small signal equivalent circuit will have only the AC source, which is 5 sin omega t millivolts, and diode will be replaced with a diode equivalent circuit. So we know that for a diode, the equivalent circuit is diode resistance RD in parallel with the capacitance of the diode. Here in fact, the capacitance value is also given, which is 0.5 nanofarad. So let me just put it here, 0.5 nanofarad, whereas RD is something we need to find. So we know RD is equal to eta Vt over ID, where ID is the DC bias current. In fact, when they have given 26 microampere is flowing through the circuit, which is DC current, that is this DC bias current flowing through the diode. Hence we can take eta is 1 times 26 millivolts Vt divided by 26 microamperes. So we have Rd is equal to 1 kilo ohm. So we can take the equivalent circuit of the diode to be 1 kilo ohm in parallel with capacitor of 0.5 nanofarad and a 100 ohm resistor here. Now we need to find what is the AC current that is flowing here. Obviously that will be equal to IAC will be equal to the input AC source divided by impedance offered by this part of the network plus the resistance of this network. We can write this as 1 kilo ohm in parallel with the reactance of the capacitance plus 100 ohm. So first let's find this value. In this, let's find what is XC. XC is 1 over j omega c, where we have all the values. This is equal to 1 over j omega is 2 times 10 power 6 radians per second times the c is 0.5 nanofarads, 10 power minus 9 farads. So this value is equal to 2 times 0.5 is 1 times 10 power minus 3, which will be equal to 1000 divided by j. Now let's see what is this value, that is 1 kilo ohms times XE is 1 kilo ohms divided by j, divided by 1 kilo ohm plus 1 kilo ohm over j. This will be equal to 1 kilo ohms divided by 1 plus j. Now this entire quantity can be written as 1 kilo ohm divided by 1 plus j plus 100 ohms. Now let's write what is IAC, which is equal to VAC is 5 sin omega t millivolts divided by, we have this value that is 1 kilo ohms plus 100 ohms times 1 plus j, and in numerator we have 1 plus j. So now we can write this equal to 5 millivolts times 1 plus j over 1.1 kilo ohms plus j 100 ohms times we have sine omega t. Now what is asked in the question is the amplitude of the AC current. That amplitude will be the magnitude of this component. Magnitude of this value will be equal to 5 millivolts. Magnitude of 1 plus j is square root 2 divided by, let's take the 100 out, times square root of 11 square plus 1 square. Of course, here we have ohms. This will be equal to 6.4 microamperes. So the amplitude of the small signal component of diode current in microamperes is 6.4.